My name is Eric Tillman, and I'm working as a solutions engineer and Earth observation specialist at Planet. And yeah, I want to thank the organizers of the webinar for inviting Planet to talk about our approach of providing geospatial insight at the speed of change and how our satellite imagery can be used to support AI-powered geospatial analysis within the Atlas platform. So for all of you that don't know who Planet is, let me begin with some words about Planet and what we are doing. So Planet is an integrated agile aerospace and data analytics company that offers customers insights at scale powered by daily global satellite imagery. So we build and operating our own nanosatellites, delivering a continuous stream of image data, enabling our customers making better informed decisions. Here are a few highlights of Planet's still young history. Planet was founded by 3 NASA scientists in 2010, and within the following years, we have launched hundreds of our experimental versions of our nanosatellites. 2017 was a big milestone in Planet history. After launching more than 140 operational satellites, we have accomplished our first mission to deliver an update of the Earth's surface on a daily basis. Additionally, Planet acquired a sub-meter satellite system, Terabella, from Google, adding 7 very high-resolution SkySat satellites to the entire fleet. In 2018, Planet has formulated its next vision of using machine learning to deliver a queryable Earth. And in 2020, so last year, additional SkySat satellites have been added to the whole constellation, enabling a high revisit of certain locations up to 7 or 10 times a day. And the first new Planet SuperDove satellites have been launched as a first step towards our next generation constellation. So just 2 weeks ago, more than 40 of these SuperDove satellites have been launched, added in order to reach daily coverage within the next few months. And within the upcoming years, we are aiming on accomplishing our vision of the queryable Earth by adding more analytics to our portfolio. And we are also working towards a better integration of our imagery with public missions like Sentinel or Landsat. So what we have seen so far is that at the end of the day, it's all about having the right data at the right time and being able to make informed, timely decisions. So free satellite imagery solutions are often too low in resolution to detect small changes around assets and infrastructure you care about, and too infrequent to proactively assess risks, detect fraud, or get updated business insights. Meanwhile, drone imagery, aerial photographs, or very high-resolution satellite imagery are often too expensive or operationally inefficient to cover vast areas and over frequent intervals. So without the right data, you're lacking the insights you need to make better informed management decisions and appropriate risk assessment. We at Planet think that there is a better way of serving your business with the right data at the speed of change. Our mission is to image the whole world every day, making change visible, accessible, and actionable. Here you see one of Planet's satellites, the so-called DAF. It's about the size of a shoebox, 10 by 10 by 30 centimeters and just 4 kilograms. We build our satellites in-house, and we are constantly innovating and incorporating the latest technology into these small satellites. They are all capable of capturing spectral reflectance in visual and near infrared of the spectrum at 3 meter spatial resolution. Our most recent version of the sensor provides 8 spectral bands, most of them especially beneficial for detecting vitality change in vegetation. Additionally, we have a constellation of 21 SkySat satellites which are capable of multispectral imaging at 65 centimeter ground sampling distance, allowing us to generate an image product with 50 centimeter resolution, providing a very detailed insight. As mentioned already, we have launched more than hundreds of our nanosatellites to create a constellation operating like a line scanner of the Earth rotating underneath, capturing images everywhere on Earth almost every day. All of these satellites are operating on a sun-synchronous orbit with a relatively fixed acquisition times. 15 of our SkySat satellites are operating on a sun-synchronous orbit as well, and 6 on a more inclined equatorial orbital plane. For those 6, the acquisition time varies from day to day, but the benefit of this orbit is that it allows us to capture individual locations on Earth multiple times a day. So these are the main features of Planet's monitoring solution. Our always-on satellite constellation collects imagery over the entire landmass of the globe on an almost daily basis. You don't need to place any tasking orders, then wait days for delivery. This saves you time and effort, and the imagery is available when you need it. Almost daily monitoring at 3-meter resolution ensures an up-to-date broad area overview of all the assets you care about and allows you to detect and respond to changes as they occur. All data collected is published in Planet's cloud-based platform within 24 hours and can be easily accessed via our online GUI or through our APIs to pull imagery directly into the tools and workflows you are using. This is an example demonstrating why high cadence imaging capabilities matters. In April 2020, the Sentinel-2 satellites from the European Space Agency were not able to capture a single useful image over the area of the Polish National Park Biebrza, while a forest fire was raging and destroying large areas of ecologically valuable forest and marshland. Whereas Planet could provide almost cloud-free images of the region before, during, and after the wildfire event, allowing for a quick assessment of the situation before the fire started and of the damaged area afterwards. And why spatial resolution matters becomes pretty obvious when you're looking at these 4 images, captured by different sensors at different spatial resolution over a plantation area in California. On the left-hand side, you see images captured by Landsat 8 and Sentinel-2 with 30-meter and 10-meter resolution respectively. Types of ground features like vegetation and roads are distinguishable, but you cannot identify the rows of trees. In the 3-meter Planet scope image, smaller features are starting to be evident. Rows of the trees are visible, and even the spatial variability within the plantation can be mapped. On the right-hand side, you are seeing the 50-centimeter SkySat image of the same location. Here, even individual trees can be clearly detected and counted. Often appropriate image selection has a trade-off between cadence, spatial resolution, and scalability. Here you see an area of 115,000 hectares, which can be covered easily on one day by means of medium or high resolution satellite imagery. And this is the approximate area which can be captured by a drone on one single day. You would need almost 600 drones to cover the entire area every day, or 1.5 years to cover the area once by one drone. And I think it's obvious that this is hardly possible and for sure not an economically efficient approach to get continuous updates on what has changed on the ground. Rather than following this inefficient approach, our proposal is more to use a combination of different imaging platforms in a kind of tip and queue approach, so that you can focus on areas that are most relevant to you. Let me quickly explain you how that works. Imagery captured on a high cadence and medium resolution is used for continuous monitoring of large areas to identify change over time. Once change has been identified, a very high resolution satellite imagery or a drone flight can be ordered over this particular area in order to get more detailed insights into what's going on the ground. This helps organizations to efficiently allocate their financial and human resources while keeping the situational awareness as well as maps and asset inventories up to date. Automated feature and feature change detection is paramount to enable an efficient tip and queue workflow. As mentioned before, Planet is working on adding more image analytic capabilities to its portfolio on a pathway towards accomplishing the vision of a queryable Earth. Here you see the different analytic feeds we have developed already, using state-of-the-art machine learning procedures. The object detection feeds for ships and planes are leveraging the daily 3-meter imagery to provide insights into pattern of life within harbors, along coastlines, and on airports. Our building and road detection analytic feed provide a monthly updated foundational layer over broad areas, which is used as well as the basis for our first change detection products, the road change detection and the building change detection. Both of these change detection feeds will enable customers across many different industries to continuously monitor large areas to find the signal of infrastructure change, to save significant time and resources, and to surface the changes that really matters to them. To introduce the key factors of this tipping queue approach, I'm going to present building detection and building change detection on the next slides. With Planet data that you can see here, you can already see all the changes in the imagery by flipping through a time series of images. However, we don't want you to have a look at all the images or to process all the data to identify change, but rather have you get direct access to what matters most to you. So how we do it? With deep learning models applied to Planet imagery, we classify the objects and feature classes you're looking for. We do this across time, and then we filter out false detections automatically. Our algorithms separate meaningful change from other noise sources, leaving only the relevant persistent changes in our change feeds to point you exclusively to those interesting locations, enabling you to focus your investigations only on what's suspicious by tasking a very high-resolution SkySat satellite or organize a drone flight campaign. Here you see an urban area in a 3-meter planet scope imagery. And this is what the foundational building detection layer looks like. The spatial resolution of the imagery does not allow for mapping exact building footprints, but it provides insights where buildings exist, and using this information across time allows us to identify areas where the buildings have been built. We have built an analytic viewer on top of Planet's APIs that helps users to visualize the change detections and guide them through the process of monitoring a large area. What you are seeing here is a heat map showing where most new buildings have been constructed in the month of August in Afghanistan. It already gives you a high-level overview of where to focus your attention in this region if you are looking for new buildings. Zooming into a specific area near the city of Herat that has experienced significant changes over time provides significant insights on a more granular level. And zooming further into the area provides you an overview of all indications where new buildings have been constructed over the course of the last month. Global mapping companies looking to regularly update their maps benefit significantly from this change detection product. Instead of remapping everything with a grid search approach, they can focus only on areas that have changed, saving time and effort. To make the tipping queue workflow as smooth as possible for our users, we have built an easy integration of the analytic viewer with our tasking dashboard. That allows you to simply click on the detection here in this viewer, which will take you directly to our tasking dashboard, where you can place an order for our 50-centimeter SkySat image for it to be captured in the next days. So the building change detection product shown before showed the change detected in August. So let's compare the situation in August on the right side with the situation 2 months before on the left side in a 50-centimeter SkySat image. It can be clearly seen that on the right side, several building structures are visible that were not there at all in the image captured earlier. This high-resolution SkySat image can be used now inside the Atlas platform to detect building footprints more accurately in order to update the maps. Yeah, with this I have reached the end of my talk, and I want to thank you for your attention. In case you are interested in learning more about Planet and how to access Planet imagery or Planet analytics, just reach out to us, sending us an email or reaching or visiting our website. Now I will hand over to Alexei, who will show you in detail how to do territory segmentation and feature extraction from Planet satellite imagery within the Atlas platform. Yeah, so Alexei, the floor is yours.
Thank you very much, Eric. Thank you. So let me share my screen and I will continue. Just a second, please.
You are already in Q&A. Yes, so the screen is on.
Yeah,
Thank you.
great. So let's continue. And actually, one of our goals for this webinar is to demonstrate to you how you can increase your efficiency by using satellite images, because, of course, in many situations, satellite will outperform drone surveys. So, what is Atlas? Actually, this is the second episode of our series of webinars about Atlas, but for those who listen about Atlas for the first time, I will give a quick introduction about myself and about Atlas. So I'm the head of software development at SPH Engineering, and I'm also a product owner of the Atlas. So at Atlas, it's a data management platform which helps you to store, share, and analyze different special products, like just normal images, orthomosaics, elevation. So all the things that you can obtain either from a drone survey or from a satellite. So let's start from some fundamentals. And I will give you just a quick overview how Atlas looks like. So it's a web-based application, web-based platform, which helps you to organize your images, your elevation models into projects. And then for each project, you can create multiple data sets, and each data set can be bound to a certain date. And you can build a timeline and compare different you can compare images for different dates and time. So you can either upload an orthomosaics to Atlas, or you can build orthomosaics from raw images in Atlas. And also, as you can see on the screen, you can also upload elevation model and store it in the context of the data set. And as I already mentioned, you can have as many data sets within one project as you want, and you can have as many projects as you want within your organization account. Also, Atlas provides different means to control access to your project data, so you can configure access to your colleagues or to your partners, clients, and use this web-based application to provide the special data to your entire team. So just to summarize, what the key things that you should remember about Atlas. So it can work with data from drones and satellites. The main formats that we work with are like PNG, JPG, GeoTIFF files. We work with images, orthomosaics, and elevation. And Atlas is a platform which optimized for terabytes of data and for hundreds of users in organization. And it's a web-based platform, so it means that it works in all modern browsers and even in mobile browsers. So you can use this in the office, in the field, whenever you want. So, but of course, the main functionality of Atlas platform is the ability to make smart data annotation. So this means that we provide manual tools for annotating orthomosaics and generating vector layers on top of it, or using AI to build your own custom object detection and territory segmentation models that will automate certain things for you and will significantly boost your productivity. So, and again, just a quick overview, how AI works. Basically, to train your own model, you need to show what you want to detect to AI, and AI will try to find similar objects based on provided examples. That's it. Very simple idea. Of course, implementation is a bit more complex. So this diagram shows a very basic workflow that you need to remember if you want to start using AI for your operations. So this workflow applies to almost all object detection tasks. So to train your own object detection model, what do you need to do? So first thing, you need to manually annotate several data samples on your data. Then you need to train AI model, and that is what Atlas. That's what Atlas will do for you. So here you need to press just one button. Then, when training is complete, you validate training results. And if you're not satisfied with training results, you repeat first two steps. So you can improve annotation somehow, either add more annotation or fix some problems in your existing annotation, and then press train button one more time. So when you're satisfied with results, you can apply this model to the remaining part of your data. And this is something that already was demonstrated today, that like the resolution and ground sampling distance matters a lot. Because when you need to find answer to the question, can I detect a certain object on orthomosaics, you just need to compare the ground sampling distance that you have with the physical size of the object. Because, for example, here's an example how you will see a car on different images with different ground sampling distance. For example, in case of 50 centimeters per pixel, the width of the car, for example, the physical width of the car 2 meters, this means that the width of the car on the image will be only 4 pixels. If ground sampling distance 15 centimeters, this image in the middle, the car will be a bit more visible and a bit more sharper. If you have 3 centimeters per pixel, the car will be you will see all the details of the car, but nothing, nothing is for free here. So nothing is for free because, of course, when you obtain data with drones, you spend a lot of time. For making the survey. Of course, you get a high resolution data, but sometimes, and in many cases, especially when you need to identify objects with a large size, you just don't need this high level of detailization. But at the same time, you might want to cover a larger area. And in this case, of course, satellite data can be far more better than drone data, and you will far more faster get result. And especially, so as Eric already demonstrated that, like in past few years, when you try to use satellite data, you could like get 20 or 10 meters in 1 pixel, which of course too large. But now with Planet data, you can get data with 3 meters per pixel and even 50 centimeters per pixel, which is sufficient for many applications. And in a few minutes, I will demonstrate you several examples how you can make a territory segmentation of the Planet data with Atlas. Another important thing is that, as I already mentioned, one of the most important parts of the workflow is the data annotation. So that's what, if you want to use AI for your practical applications, you need to understand that the quality of your results will depend on the quality of your data annotation. And typically, when you need to specify for the neural network what you want to detect, You specify two things. You need to specify what is the object of interest for you and what is the background. So that will enable neural network to distinguish between your object of interest and all the remaining things which are not your object of interest. So that is why in Atlas, we have tools which allow you to specify a background for a certain class, for a certain type of object, and the object itself. And it's very important. And this, on this picture, this dashed line specify the background area, and the solid line specify the object of interest. But the annotation is not very good because the background contains, for example, sorry, I just missed a very important thing, that in this specific case, we want to identify scratches on the asphalt surface. But in this specific example of annotation, we have a lot of scratches not annotated within the background area, which is not good. Here, we have another example that we annotated scratches, but we didn't specify the background area. And here, again, it's more or less good, but the accuracy of object annotation is not very good because a large part of good asphalt also annotated as a scratch. And this last example is an example of a good annotation where scratches identified, annotated more or less accurately, background is accurate, and that gives you a chance to get a good result. So now the boring part is over. Now let's see how can we analyze the planet data in Atlas. So the first example, the NDVI map segmentation with GSD 3 meters per pixel. So this is how it looks like in Atlas. This is a web-based interface, and I uploaded the data sample from Planet. So I calculated the NDVI index on top of the multispectral data provided by Planet. So this is how it looks like. And now you will see that I repeat exactly the same workflow that I just explained to you. So first thing, I use our tools to identify the red areas, the areas with some problem. And I add some manual annotation to specify for the system how it should look like, And I add the class name. Then I specify the background area. Yep. And I fix it a little bit, and I add more background areas with just green color to specify more information about the background. Then I press. Then I start training, but before that, I specify the working area that will be used to test my train detector. Then I press train, and the system trains the model for me that will try to identify these red areas. And here is the result of the segmentation of the working area. I will put on pause for just for a second. So here, the polygons that you can see on the screen generated automatically by Atlas. So the red areas annotated properly, and for each area you see the area size and location. So, oh, excuse me, it seems like I just skipped. So let me return back. Yep. So then I can export this vector layer as a GeoJSON file or DXF, and you can use this data for some further analysis, or you can use this data, for example, to send it to a drone pilot, and the drone pilot can approach these locations one by one and get a closer look what happens there with the drone. So, and that significantly will reduce the amount of work that has to be done, because otherwise one may spend a lot of time just to obtaining information about where this problematic zones exist on your field. So, and actually for this specific example, it took, I don't know, something around 30 to 40 minutes to build the first version of the detector that generates this vector layer. So it's pretty fast. Then let's see another example. Now in this case, we will use a more detailed data. We will use orthomosaics with 50 centimeters per pixel GSD, and we will use it for tree counting. So here is the set of fields, and we will try, and of course each field looks like a normal regular plant. So trees have more or less the same size, and they planted more or less uniform. So we will try to build a model that will help us to count number of objects. So let's see. So first of all, again, I do some manual annotation, and I use our Magic Wand tool that helps you. That's a smart tool that helps you to annotate fast a very different objects. So you don't need to draw polylines manually or circles or something like that. You just click on the object of your interest, and it is being highlighted by our tool. Then I specify the background area and start training. And after training, let's see what happens. So yeah, this is the result of the segmentation. And I put it on pause for a while just to show you that, yeah, at first glance, we see that the territory segmentation algorithm, it generated polygons, which include just not a single tree, but sometimes this algorithm merges several trees which stand nearby, and when the color, when the level of sharpness is not that big, so it's very hard to distinguish and separate one tree from another. And of course, this data, it cannot be used just to properly count trees, but that is just the first step that enables us to separate the background, the area between trees, from the area covered by trees. And then we can, sorry, seems like again, seems like I just jumped to next slide. So let me show you again. So, but then we can apply our post-processing algorithms that helps to identify each individual tree. And I hope you can see these red dots. So now this data can be used for counting, because we get a more or less accurate model for this field, and we more or less estimate of the number of trees on this field. And again, the overall training for this example, it took just 40 or like minutes or 1 hour to generate the first version of the model. And of course, the model can be significantly improved and be more general for various types of trees. And also, what is more important, because in a single area, you might have very different fields with mature trees, with young trees. They may have very different size and look, and you may, it's not mandatory to generate just one detector. So for different classes of objects on a single map, you can have different detectors and different labels. So that will allow you to improve performance of each individual detector. So just keep it in mind when you will play with data. So let's see what is next. Another example, building counting. So you can also use 50 centimeter data to count buildings, because this resolution is sufficient for separating normal buildings, I mean, something which is more than 20 or 30 square meters, then I think this building is identifiable. So this is a result of this algorithm. And as you can see, of course, the building footprints, maybe they're not very accurate because the resolution is a bit bigger for an accurate, bigger than needed for generating a very accurate building footprint, but it is sufficient for making an accurate counting. And as you can see, so you can surround the area with a polygon and see how many objects of a certain type exist in this area. Another example, you also on the data with 50 centimeters per pixel, you can generate road contours. And for this task, you don't even need to train machine learning algorithm. At least you can begin with our smart annotation tools. If you need to cover a large area, or if you want to automate it additionally, then of course you can train a detector. But here I want to show you how to use our smart annotation tool for generating contours. So see how it looks like. So you just click in different points of the object of interest, and in our web client, we generate automatically the contours for this object. And you can control the, you know, like the threshold that affects how sensitive this tool for the color change. Also, you can use manual tools just to polish a little bit and to remove some unnecessary parts. Also, you can minimize the number of points in your polygon and make certain parts more straight. So, and I think I just I think I set the speed so I played at a so just 2 times faster than I did it in reality. So it take for this area, which is several hectares, it took like a few minutes for the first rough draft of the road contours. Of course, you can polish it later, and also you can export this data as a DXF file and then play with it in your favorite GIS or CAD tool, like, I don't know, Autodesk Civil 3D or S3, ArcGIS, or I don't know, whatever you want to use. So that's another example. Let's move on. About deployment types of Atlas. So we offer Atlas in 2 forms. It's available as a cloud-based service in our cloud, so you can subscribe to it, or you can get it as an on-premises software and deploy it to a data center or your private Amazon account or Microsoft Azure account. In this case, all the components of the software will be deployed locally, so, and it will not require internet connection except for the license activation. And for Atlas on premises, you can start from the very moderate system requirements for the hardware. So you just need a couple of computers, and I would say that the minimum requirement are equal to requirements for modern high-performance gaming PCs. So of course, if you work with a lot of data, you need a good storage. But again, these days it's not a problem. So actually, you can easily start with your own installation of Atlas on premises. So actually, it seems like we are almost out of time, and I almost finished my presentation, and now I'm ready to. I and Eric, we are ready to answer your questions. So if you have any, please type in Q&A and we will try to answer.
Yes, thank you, Eric. Thank you, Alexei. So we have one question in the chat. Does Atlas only accommodate satellite data or any other aerial imagery?
No, you can. We can use data from drones, so you can upload just raw images and into gallery of images and build a detector on top of this. I don't know, on top of hundreds or thousands of separate images, or you can upload orthomosaics to Atlas and analyze it.
And another question in the Q&A section about building facade defects. Can they be automatically detected using Atlas? And how much training is required?
The answer is yes. Such defects can be identified with Atlas. So that depends on the type of defect, how visible this defect, and how many samples and do they look similar to each other, or they're very different, and do you work with very different surfaces? I mean, the texture of the surfaces, is it the same? I don't know, concrete or glass, or that also may affect the training speed. But again, as I already mentioned, so the first results with a very accurate annotation can be obtained in several hours. So the prototyping phase is very fast here. So you can upload your data and try it. And if you know how to annotate, and we have special training articles where we explain in details how to work with the system. So if you will spend, say, 1 hour for learning basic concepts, and then you will spend, say, 1 hour for data annotation, accurate data annotation, and 1 or 2 hours for training, maybe 1, 2, or 3 iterations. I'm pretty sure that you will get some good results.
So what's about thermal data for Atlas?
In case of thermal data, we can work with JPG files. We cannot work with TIFF files right now.
Yeah, there's one question. If planet data can be used to create 3D maps to be used in mission planning for terrain following applications. So the answer is twofold. I mean, we have 2 different constellations that I've presented. So we have this 50 centimeter SkySat constellation, and those satellites are capable of collecting stereo images. So that means with one overflight over the location, they can capture so quickly so that they can generate 2 collection stripes, and those can be used in 3D or photogrammetric software. There's also it's just recently published a scientific paper that is showing how that is how you can use this data to create 3D maps. And for the planet scope data, so the 3-meter resolution data, this is not a stereo imaging satellite, but so I talked to one of our clients, and I saw also a scientific paper, so that it is possible to use imagery from different dates, so that were captured over the same location. You can use them while you select appropriate images that overlap in a certain to a certain degree, and then you can ingest those also in photogrammetric software to produce 3D or digital terrain models. It always depends on the quality of the height differences you want to detect and so on. But in general, it is possible, yes.
So can Atlas detect work on vegetation change detection in vegetation across years? Do we have something done already?
Atlas can be used to identify vegetation. If you need to identify different classes of vegetation, then I think that's what Kurt asked us. So in this case, you will have a dedicated detector for each vegetation type, but you can run these multiple detectors on the same data set, on the same map, and the software will generate different layers for each type of vegetation. So I think that's the first part of the answer, and the change tracking. Actually, yes. So in Atlas, so if you obtain data for the same territory multiple times per year, so you can upload this data to Atlas. Actually, you will have some functionality even in Planet user interface, because Eric demonstrated that. But in Atlas also you can upload data for the same area, and you will have a timeline. So you can apply detection for each data set, and you will see what have changed in time. So again, so the answer is yes.
Nathan asks if this is a time saver for power line vegetation encroachment surveys.
In case of, I think in case of encroachment surveys, you need the elevation model. I mean, you need heights of the vegetation. So with drone data, you can build this model, and in Atlas you can analyze elevation. Actually, we had a webinar 2 weeks ago where we demonstrated what you can do with elevation in Atlas. But Eric, do you want to add something regarding elevation in case of Planet?
Yeah, actually, I want to add something to the power line vegetation encroachment detection. So this is a typical use case where our data is used. So this kind of a tipping queue approach that I've explained is that you use the 3-meter data to monitor vegetation using NDVI, for instance, and you see, or over time, you can identify areas along this power line in the certain corridor that are changing over time. So meaning in this case, vegetation is, or biomass is increasing. So that doesn't mean that it is dangerous for the power line, but okay, something is going on. And then you can go there or task either a 50 centimeter satellite. This is what our clients are often doing. And just to get a more detailed view, or, I mean, you can send out the drone to this area, because you could narrow down the area of interest and send a drone to this place, saving you a lot of time. And then you can get, with this drone imagery, very detailed insights. But the 30 centimeter is often good enough to, I mean, even you don't have the height, yeah, but you can see if the what kind of vegetation it is and how tall it is. And I mean, tall in theory, you can identify it based on the shadow and so on. I mean, if you are familiar with the vegetation, you can judge that.
I see another question from in Q&A. Does Atlas support point cloud data? And for now, no, but in 2 months, we will support point cloud data, and also we will support additional features for construction areas, like cross-section diagrams and 3D mesh comparison. So just stay tuned, and we'll monitor our release notes about the training areas. In most cases, we work with RGB images. So we use, when we train a detector, we use color and texture information to train the detector. And the deep learning algorithm, it makes a so-called feature extraction. and it tries to understand how to properly generalize the domain of objects that you provided with the training data. Hope that answers. So not a wavelength, but just the data in image channels.